the ideas of Einstein, that why he thought that, so the second part will then be concerned with the ये इस तरह करें वहाँ से स्टूल लें आप लेफ्ट से स्टूल लें. What is general relativity? Little bit about the word general. I will show you that why Einstein had to choose this word general relativity. Actually, there are two theories of relativity, which were both of them were formulated by Einstein. The first one was special theory of relativity, and the second is general relativity. Special relativity was formulated in 1905 in two papers by Einstein. And general relativity is kind of generalization of this special theory of relativity, which is then almost 10 years after the special part. That is called general relativity. And the reason for this choice of the word is that in special relativity we deal with only inertial frame of references. That is, those frame of references are those observers which either are at rest or move with certain constant velocity. Or formally you can say that Newton's first law of motion, that is, if there is no forces then there are no acceleration, holds in such frame of references. So this is a special choice of a frame of reference, therefore this is called special theory of relativity. But those frame of references where there is an acceleration or which move with certain type of acceleration. For example, you feel this every day when you are sitting in the car and suddenly the car stops or starts running, then you feel some kind of jerk on your body. This is because of this acceleration, and that produces a force on your body, and this frame of reference is not inertial then because it has an acceleration. These are called non-inertial frame of references. So Einstein thought that there is a theory which deals with the only inertial frame of references. This is called special relativity. And why not to have another theory which includes also the non-inertial frame of references, and then he named it as a general theory which includes all sorts of frame of references. So this is somehow the meaning, the reason for the word. But certainly the general theory of relativity is the theory of gravitation. We will see. Special relativity is not a theory of gravitation. It is just the theory of space and time. It explains to you how the two space and time can be treated together. But general relativity tells you what is gravity. So, didn't we know before general relativity what gravity is? Certainly we knew that gravity with the virtue of Newton's law of gravitation. Sometimes we call it Newton gravitational or Newton gravitation. And this is very famous and very simple equation. You all know about it. And you all know this fairy tale that when Newton was sitting under the apple tree and the apple falls on his head, and then he thinks why the apple is falling, and he concludes that because Earth is attracting an apple towards itself, or any two objects in this universe will attract each other with this force. So Newton is telling us that gravity or gravitation generally is the force between two objects, the attractive force between two objects. And this G is the constant which determines the strength of this force, and these are the two masses, and this is the inverse square law as you know. So this is the answer for the gravitational attraction between two forces coming from the Newton's law. But there is a basic problem with this law. What is that basic problem? This was one hint which we already had, even in the Newton's time. You can अपने लिए स्टूल ले लेफ्ट से, फिर यहाँ लेफ्ट से स्टूल ले. So the problem is, you might know that the failure of Newtonian gravitation was actually this precession of Mercury's orbit. As you know, in solar system, the Mercury which orbits around the Sun its orbit actually also revolves around the Sun. For example, if Mercury is revolving in this orbit, after some time its orbit changes to this orbit. So there is also an angle here with which it revolves around the Sun. All planets do this. But the problem is, if you calculate that how this is called somehow the precession of Mercury orbit. If you calculate this deviation from the original orbit, you have to include so many factors. One of the factors is that near the Mercury there is certainly another planet, Jupiter or Earth, which are also applying force of gravitation on this planet, and because of their attraction, if you include that in attraction or that force, the planet orbits, the Mercury's orbit changes. Similarly, Earth's orbit also changes, the other planet's orbit also changes. But the problem is, if you calculate from Newton gravitation, the change in this orbit, this does not match with the experimental results. And nobody knew why. So this was sort of a small hint, experimental hint at that time, that there is some problem with the Newton's idea that the two bodies attract each other, and this is the gravitation. This is the source of gravitation. Like there is something hidden in one object, or for example, there is something hidden in the Earth. Because of the virtue of that, it attracts any other object, for example me, or for example this object towards itself. And this idea has some problem, because if it had not any problem, then this precision we should have calculated accurately. But I tell you that the Einstein idea was not exactly, the Einstein motivation was not exactly this thing, that there is a problem with Mercury's orbit. There were other thought experiments which Einstein has done, but at least we had experimental clue that something is wrong with Newtonian gravity. Now, Einstein had many experimental and many thought experiments. And this slide I have put over here just to give you first the two postulates, and then after this I will explain how Einstein reached to these postulates. Fortunately, the general relativity has only two postulates. One is called the principle of equivalence. This is the core essence of the general relativity. This is sometimes called the strong equivalence principle. I will show you in a moment a weak equivalence principle as well. But at least you know that there are two postulates, which says the strong principle of equivalence says in the vicinity of any point, a gravitational field is equivalent to accelerated frame of reference. So Einstein said that acceleration and the gravitation, these are the just same things. There is no difference. That's what equivalence means. But this is a strong equivalence. I will show you the weak equivalence as well, in the absence of gravitational effects. And the second, this is the very basic understanding of all the physicists. That the law of nature have the same form in any frame of reference, whether accelerated or not. It means that the laws of physics are not different for me and different for you. The laws of, I am an observer, you are an observer, either I am accelerated or not, I am at rest or not, whatever. But this cannot happen that energy is conserved for me and not conserved for you. This cannot happen. Because law of conservation of energy is the law of nature, and it is not dependent on observer. It does not change observer to observer. For example, Newton's second law, F is equal to ma, this also does not change. Gauss's law, or the law of conservation of linear momentum, all these laws of nature, these are laws of nature, they are independent of whosoever is observing them, and with which velocity that observer is traveling. This is the basic principle of all the physics. And also, Einstein made it the part of his postulate. This is the second postulate, but the essence lies in the first postulate, where it says that there is an equivalence. Let me take a few minutes in order to understand what this equivalence means. The equivalence principle, by the way, I am at the moment talking about the strong equivalence principle. I will come to the weak equivalence principle as well. That there is no experiment that can be done in a small confined space that can detect the difference between a uniform gravitational field and an equivalent uniform acceleration. For this thing, Einstein had done the thought experiment. or Gedanken experiment, which means you are just imagining. And this was the power of imagination of humankind. The Einstein's imagination was strong enough to do an experiment in the space, just to imagine an experiment in his mind, and come to the conclusion, and come to such a conclusion which has such a profound consequences that even 100 years after that we are now appreciating this theory, general relativity, which was just came out of his imagination. And this is the weak principle. I will show you his thought experiment later, but this is the principle of weak equivalence principle. And what it says that if there are two forces acting on certain mass, this is very common day experiment, and we take it as granted, but it is not granted. For example, there is a mass on which there is some force is acting. For example, I am applying the force on this dice, for example, or you are applying a force on certain thing, or you are in a car and car is applying certain. This mass